Okay, so now we're all on page 18 and we're looking at relative atomic mass. And just a bit of a reminder about what relative atomic mass is. Here we have a periodic table. And what we're talking about really is the number at the bottom here, isn't it? This is where we record the relative atomic mass. You can see here in the key to how you read this periodic table is down there. The mass, the atomic mass, is made up of the number of protons and neutrons that are present. If, like the electrons really contribute nothing, effectively nothing to the mass. So it's the combination of the protons and neutrons, which have to be present in whole numbers. You can only have integers. You can't have 1.5 protons present, as we talked about last time. But the reason why these aren't whole numbers is because this is giving us the average of the percent of each isotope as it occurs in nature. So we can see that, like with chlorine, 35.45 is the relative atomic mass of a bog standard sample of chlorine from around the world. It's made up of two isotopes, chlorine 35 and chlorine 37, and they're present in the ratio of 25% to 75%, approximately, okay? Which then gives us this 35.45. So if it's chlorine 35 and chlorine 37, then we can see that it's the 35 that is more abundant than the 37 because the average is closer to 35. Does that make sense? And it depends on how many different naturally occurring isotopes there are and the percentage that they are found in as to what this relative atomic mass is given. We can calculate that if we know which isotopes we need to be calculating with, and that's our example here on page 18. The first one is for magnesium. And we've got the 3 isotopes of magnesium here. Magnesium 24, 25 and 26, and we're told the different percentages in which they occur in nature, and we can then calculate the relative atomic mass. So for 24, we've got 78.7%. Now, you could write that as 78.7 divided by 100. That's for the 24, and then we've got 25, and there's 10.1% of them. You could also write it just as the decimal, 0.101 plus 26 times 0.112, and this decimal way would be my preferred way. It's just tidier. I'm sure you all understand how you arrive at the decimal when it's expressed as a percent. And you can see then we add them all together, 18.89 plus 2.53, which I wouldn't write this line out. I wouldn't write it out in a calculation because that's really enough working, which then gives us 24.33. That was this is 4 sig figs. But all of our percents were given to 3 sig figs. So we're then going to change our answer to 24.3 so that it's to 3 sig figs to match the information that was given in the question. Okay, so that's for an element. We use this same thinking, if you like, when we're calculating the relative molecular mass for compounds. We're just adding together the atomic masses. So I want you to use this format when you're writing your working out for your calculations. The capital M for the molecular or molar mass. In bracket, you're going to write what you're finding the molar mass of. And then you can write out your calculation. We need the atomic mass of hydrogen. In the booklet it's telling you to round. I tell you now, don't round. So write the numbers as they are written on your formula sheets. And you might also notice that I'm even writing zeros. Okay, write your zeros down. This is a reminder for you sig figs. I know that oxygen is just 16, and that 16.00 rounds to 16, it's the same number. And if I'm putting this in my calculator, I will only put 16 in the calculator. I won't put 0.00 because that would be a waste of time. But I write it down because this is all to do with significant figures. And so my value, I reckon, that's in the booklet is going to be slightly different to what we would calculate. 1.08 plus 14. We used to have all these rules about which numbers, how much to write them, how many decimals to write them to. So that would give me 63.018, which really would be 63.02, because these ones only go to 2 decimal places. I'm just going to round that to 2 decimal places. Our second example is to calculate the relative molecular mass of glucose. Same process and the same setting out, please. So the capital M, say I'm calculating the molecular mass. It's going to be 6 lots of carbon and 12 lots of hydrogen and 6 lots of oxygen. And do you remember, when we say relative, do you remember what it was relative to?
12.
We're getting there a little bit. Relative to?
It's relative to anything.
Well, no, it's not. It's not relative to anything. Now again, because I've only got 2 decimal places, I'm going to need to round this one 2 decimal places. Relative to 1/12 of the mass of the carbon-12 isotope.
Yeah.
That's what it's relative to. And we've got one more example, which is our hydrated one on page 19. Water crystallization. So not all of our ionic compounds are just as they're written. For example, the copper sulfate, which we would just write like that often, and we use the blue crystals out of our container with copper sulfate. It's actually copper sulfate pentahydrate. So this is a reasonably common thing that our ionic compounds can trap water within the lattice. Look at this example though on page 19 where we're looking at the hydrated magnesium sulfate. So it's MgSO4.7H2O. And we want to find the molar mass. And it's best to calculate them separately, because if you're asked to find the percent water or something like that and you've combined all of your oxygens together, for example, then you've got to start back at the very beginning for your calculation, so keep them separate. So we want magnesium then, 4.3 plus sulfur, I think it's actually 32.06, 4 times 16 plus, and then can do 7 lots, so 2 times 5.00, 8 plus 16 times 0. I don't really mind how you do that part. That's probably how I would do that. And yeah, like I said, good idea to get the ants to this part and the ants to this part separate, so that if there is a part B and where you need to do those calculations of percent hydration or whatever, you can do it more easily. Right. So let's do that. What you got? We like that. And obviously we add them together to get the final answer, the 24647. All right. Yes?
Do you go to decimal places or sig figs?
Because we're adding, it's decimal places. The moment we multiply or divide, it's sig figs, but addition and subtraction, it's decimal places. Yeah. Any other questions?
How many sig figs are we expected to go to?
Well, for this one, because we're adding, it's decimal places, and so it would be to the least number. Now, I know I've cheated a bit here, but I didn't look that one up. I looked that one up. Can somebody tell me where it is? Where?
24.31.
3-1. Okay, so because I'm adding them, then I'm only going to end up with an answer to 2 decimal places because only one of the values goes to 3.
So what's the difference between sig figs and decimal places?
It's that measure of uncertainty, and it depends on whether you're multiplying, dividing, or adding and subtracting.
So it's the same.
It's all about uncertainty. How you arrive at how you're going to answer is dependent on the calculation. So the moment that you're multiplying and dividing, you're going to go for sig figs, even if there's some addition in those steps.
Yep.
All right. Okay. Let's work on some questions again then.